Let us now look at various types of differential equations, starting with the lower order ones. So, as a differential equation with its lowest possible order, we will start with first order differential equations. We have already seen one example of a first order differential equation in what over here. A general statement of a first order differential equation would involve a first order derivative of the unknown function, which I will choose henceforth as y, as a function of a variable which I will choose as x. Hence, we could expect the differential equation to involve first derivative of y with respect to x, indicated by dy by dx, and it will in general be stated as a function of x and y. Observe that on the right hand side we could expect lower order derivatives of the unknown function, which in this case is the 0th order derivative, the function y itself. Of course, if you have a differential equation of this type, in general, there are situations where we are able to solve such differential equations. We would see a couple of such instances where we are able to solve such differential equations, and the particular examples that we will look at would be the ones which are most commonly found in various situations in physics, and this is why I choose those two special cases for these set of lectures. So, we will begin with one of the simplest cases of first order differential equations that can be solved rather easily, and that particular case is the one of an exact differential equation. Let us see what are the exact differential equations and how and why we are able to solve it rather without much difficulty. A differential equation, as I stated, first order differential equation especially is a statement of the first order derivative of an unknown function in terms of the function itself and possibly the variable also. However, a differential equation need not be stated in this form itself. There are ways in which derivative of an unknown function with respect to a variable can be given, such as this. As you would see that if I have functions m and n both being functions of x and y, if I write an equation of this form, it is equivalent to writing derivative of y with respect to x. This can be easily checked by indeed taking one factor to the right hand side and then writing dy by dx as minus m of x minus n of x comma y over m of x comma y. Now, this type of an equation, if we observe, could be seen that under a certain condition, under certain conditions or in certain situations, such an equation becomes easily integrable, or it becomes easy to solve, and that condition we could observe is when m of x comma y is partial derivative with respect to y of certain other function of x and y, while n of x comma y is partial derivative of the same function with respect to x. Now, if m and n have this particular form, it is easy to observe that by substituting these forms for m and n into our differential equation, we get del f by del y into dy plus del f by del x into dx, which is easily seen to be nothing but the differential of the function f itself. After all, if I want to know what change happens to a function f that is a function of two variables x and y, what I should do is to obtain the change that occurs to the function f through the change in x, which is given here, or the change in y, which is given here. The net change will be a sum of the changes that happens in through changes of x alone and changes in y alone. So, this clearly tells us that if m and n have this particular form, then the left hand side is differential of a certain function of x and y, which I call f, which lets me integrate this easily and write the solution in the form f of x comma y equal to c. So, the solution will be of this form. Now, how do we know whether our given differential equation is of this form, where m and n have this particular or this special form in terms of a function of x and y? Well, if m and n have this particular form, then they must obey the following. If I take partial derivative of m with respect to x, I know that must give me second partial derivative of f with respect to second partial derivative of f with respect to y and x. However, since partial derivatives can be taken in any order as we like, it is the same as partial derivative of f with respect to x first and then y next, which itself is nothing but partial derivative with respect to y of n, because n itself is del f by del x. So, if m and n were of this form, it is necessary for them to obey the condition that del m by del x to be equal to del n by del y. The partial derivative of m with respect to x must equal the partial derivative of n with respect to y. If this condition is obeyed, then we identify that differential equation to be an exact differential equation. So, this is the condition for exactness of the differential equation. to take a quick example, we can see that choosing m to be 2x square y and m to be 2 y square x, it is easy for us to check that del m by del x is indeed 4 times x comma y, where I have taken the derivative of the right hand side with respect to x by keeping y constant, while del n by del y will be 4 times y x, where I have taken the derivative of the right hand side with respect to y by keeping x constant, both resulting in the same quantity 4 times x y, and we identify the differential equation in which m is 2x square y and n as 2y square x to be an exact differential equation, and the solution to that is also easily seen. Since we now know that m is of the form del f by del y, which is 2 times x square y, and n is of the form del f by del x, which is 2 times y square x. Now, these set of equations can be integrated either by first integrating over y and then integrating over x, or in the reverse order. Let us do the first one. Okay, let us pick this function and try to integrate it over y alone and obtain the form of f of x comma y. Well, if I integrate this equation over y alone by treating x as constant, we could see that we get integral of 2x square y dy on the right hand side, plus now since I am integrating a partial differential equation, I am allowed to add in place of the constant of integration any function of x alone, because while taking partial derivative I am going to keep x constant. So, effectively whatever function exclusively of x alone, like such as g of x, under partial derivation this would remain constant anyway. Okay. So, this will be the form of a general solution to such a first order partial differential equation, and integrating this over y alone, I get y square over 2 as the contribution from the integral, multiplied by 2x square, which in fact gives me x square y square plus g of x as the solution. So, that is the form of the solution that we get by solving only the first of the equations. Now, it remains to be found what g of x is. To find what g of x is, we can make use of the second differential equation available here. If I substitute this solution into the second differential equation for n, we see that by taking the partial derivative of this solution with respect to x, we get del f by del x to be 2x y square wherein I have taken the derivative of this with respect to x alone by treating y constant, plus derivative of g with respect to x, which is an ordinary derivative of g with respect to x because that is a function only of x. Now, we know the form of del f by del x from this equation, and it tells me that dg by dx in our solution must be 0 for us to satisfy the second equation. Or we could say that the function g of x that we have added has to be some constant c. Okay. Thus, we have a solution of the form f of x comma y equal to x square y square plus c. Please note that I had chosen c as the constant of integration or the solution for g of x. It is good for us to write it as c1 and thus write the solution as f of x y equal to x square y square plus c1, so as to be consistent with our notation earlier. Now, having found what f of x y is, substituting this into the form of the solution, we get x square y square plus c1 equal to c as the solution that we want. Of course, since both c1 and c are arbitrary at this stage, it is good to write c minus c1 as some c 0 and express the solution in this form. As it is easy to observe, this indeed gives us the solution to a certain curve which obeys the equation y equal to some constant square root of c0 over x with plus or minus. The plot of such a function would reveal that this is nothing but a hyperbola. We have seen the exact differential equations as a class of differential equation, first order differential equations that can be easily integrated to obtain the unknown function y. It's a function of x. However, many differential equations, many first order differential equations that we see are not exact as it appears, or they are not manifestly exact, due to which when they are stated in this form, it is often found that partial derivative of m with respect to x does not equal the partial derivative of n with respect to y. And since these two are not equal, we would have to conclude that such a differential equation is not exact. However, in many such cases, it is found that we could turn this differential equation into an exact differential equation by multiplying it with an appropriate function, which I would call mu of x and y, such that when I multiply with mu, the function, the differential equation becomes mu times m into dy plus mu times n into dx, where I could write this entire thing as a total differential, such that when I take the partial derivative of mu times m with respect to x, that equals partial derivative of mu times n with respect to y. If we can find such a function mu, then it is easy for us to convert this differential equation into an exact differential equation of this type. The function mu that helps us to do this is often called an integrating factor. Integrating factor. It should be noted that this integrating factor is not a unique function often. However, a class of functions would also serve as an integrating factor. We will not go into the details of this claim. So, let us see under what condition we would get such an integrating factor, and if such a factor exists, how we could find that integrating factor. In order to find what the condition that mu should obey, let us carry out this derivative. If we carry out that derivative, on the left hand side we get del mu by del x into m plus mu into del m by del x, while on the right hand side we get del mu by del y into n plus mu into del n by del y from where we could now obtain the form of mu as m into del mu over del x minus n into del mu over del y divided by carrying over this factor to the left hand side del n by del y minus del m over del x. So, if mu is of this form, then certainly we should be able to multiply the given differential equation with such a mu and obtain the solution for that differential equation. Now, such an equation can be made easier, or integrating factor which is in general of this form can be obtained in cases where mu is chosen to be a function only of x, such that del mu over del y is 0. Okay. When that happens, we could see that the right hand side becomes m into del mu over del x, where mu is a function. Since mu is a function only of x, I could very well write that partial derivative as a total derivative d mu over dx divided by del n over del y minus del m over del x. Bringing factors of mu onto one side, we could express this equation as d mu over mu to be equal to dx of 1 over m del n over del y minus 1 over m of del n over del x. The left hand side can be integrated easily to obtain ln of mu, while the right hand side, since it is a known quantity where del n by del y and del m by del x are all computable out of the given differential equation, we get mu to be of the form integral dx of 1 over m del n by del y multiplied by 1 over m minus del n by del x multiplied by 1 over, and thus we could write mu itself as exponential of this whole quantity. We would consider one example of a problem where we find the integrating factor also in our tutorials.